We've said that in these batteries, that what is happening is we are changing chemical energy into electrical work. So we need to be more specific about this in terms of the equations. Here we have our delta G, the Gibbs free energy. The change in that free energy is a measure of the amount of work, chemically speaking. On the other side, we have the amount of work done electrically. So we are always looking at this, and if electrical work is being done, it is being done by the chemicals, which means your delta G will be negative because it will now have less chemical energy inside of it. And that's also tells us that it should be spontaneous, which we expect when we hook up a battery that it's going to power whatever it is hooked up to. If we look into the amount of work done electrically, it's very similar to what I was saying about taking a heavy book, putting it up on a bookshelf. How heavy was the book? How high was the bookshelf? These are the two things that change all the time. In the case of this electrical work, it's going to be how many electrons are being moved and what is the height that they're being moved to, the voltage of the cell. Q is generally just considered the quantity of charge, and we don't usually say just an electron, okay? You may have heard, though, in physics of electron volts. That would be one electron and how much voltage it had. But that is so small. In fact, a charge is 1.6 times 10 to the negative 19 coulombs. So that's really small. Doesn't match up with the idea of the units in chemistry either, because we don't use individual electrons and we don't use coulombs normally. We use moles because individual items are so small. We have our own method. We don't go to coulombs like the electrical people do. We go to moles. So we need to have something to get us between those two. So if we take a charge and we multiply it by Avogadro's number so that we have a whole mole of electrons, then we will get Faraday's constant, that it is this many coulombs per mole. There should be a per mole in there, but it's the electrical charge in a mole of electrons. So here we have what we're going to use for Q is N, the number of moles, and F, Faraday's constant, so that we'll turn it into coulombs. So the NF will be coulombs times our energy of our cell, our voltage in the cell. So N's the number of moles of electrons. And the fact of the matter is, a coulomb volt is a joule. So we're finally at the units of energy that we've been using before. We don't want to use electron volts. Coulomb volts is the same thing as a joule. This is your zinc copper cell that we've done before. And when we did it, we noticed what E was for the cell, and we'd made it out of these two. We kept this one the way it was, and we flipped this one the other way. And what we can gather from that is what to put into this equation. What is the change in energy of the cell? Well, minus NFE. All right, well, what is that? N is the number of moles of electrons. So I just look here and say, oh, well, they're both at 2, so I don't even have to do anything sneaky. I know it's 2 moles of electrons. I use Faraday's number, coulombs per mole. That'll cancel the moles. And when I multiply that all the way through with the voltage, I will end up with this number, coulomb volts, which I now recognize to be the same as joules. And since I don't like using 10 to the 5th, I'll use the kilojoules that we typically do. So we can see that the Gibbs free energy is a negative. And yeah, this is just like when we would throw the solid piece of zinc in the copper sulfate and it would just spontaneously occur. This is the sort of energy that we would be talking about occurring during that chemical reaction.